Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about energy storage possibilities. So let's dive deep into it. Now, why there is such a talk about it right now? What is the need for it? Well, need is we practically cannot get 24 into 7 power from solar and wind alone. Basically, it's a fundamental issue. Now, are there tricks to solve it? Yes, there is one trick that if you go global, as in like if you have a international high, ultra high direct current, DC systems, yeah, then you can have like things connected. Like for example, there is a plant that is going on right now that where they will take a solar energy from Australia, dump it into UK. So that's the idea. It basically, if you have whole planet connected to a one grid, yeah, that we do not have to worry about storage. We sorted, we good, we done. But let's come to a bit more realistic reality where that problem requires you start to have some storage to solve it. You cannot solve it by brute forcing it unless you have the whole planet to cover. Another aspect is that's one problem. That's a deficit problem when you have too little power. Another problem is like it's too common, which again, a few years ago, if you have said it, people would have laughed at you or somebody would have said, hey, pass the joint, man. Is that we are reaching a point where we have common curtailments, meaning we have generation on the grid, we have to shut it off. That's sinking. We have to shut power off so we do not fry the grid. And what does grid mean? Grid simply means the interconnection of all the spinning mass that is there in the grid and all the substation, all the connection, high voltage line, transformers, things of that nature. So that's what we are talking about here. That's a overproduction. So one we have deficit, another we have surplus. Both of them are happening and both of them could happen at the same time. Basically during the daytime, peak sunlight, you can have like surplus, and during night, dead of night, your wind may not be blowing as strongly and then you're like, lol. So you no longer have power. So this is a very serious issue. So how can we solve it? The easiest way to solve is having a huge storage that can buffer it out. Basically, it has to balance it. So supply and demand curves, they are two separate entities running on two separate algorithms. Nature is controlling these puppies and humans are being run on different algorithms. So you want to make sure these two can marry. So you need a buffer stage. Buffer stage is the energy storage. That's why there is such a talk of it, because again, 15 years ago or in 2000, if you have talked to anyone, it's like, we're gonna have so much solar that we're gonna disable the power grid, people would have laughed you out of the room. That happens regularly now. So again, you must have seen a lot of wind turbines where only few are running. Why? Curtailment. Like it's a real thing that really is happening. So there is a genuine need, and need is now. So you have to understand, when we are talking about energy storage, it's not just one thing. There are vectors to it. So there are five primary vectors. First vector is scale. What kind of megawatt we are talking about? And like, are you talking about kilowatt? I have two lead acid battery that are 12 volt into 200 amp hour. So 4 kilowatt ish, so to say. So that's scale, like kilowatt, megawatt, gigawatt. So that's the scale part of it. Another is cost. Again, can I get a lithium ion battery for my solar inverter? Absolutely, if I were rich. So that's the cost aspect of it. Another is power. So how much oomph it can dump. For example, in my case, my inverter is the weak point, so it can only dump up to 1600 watts of load. If you are trying to run a small town, 50 megawatt, 100 megawatt, 200 megawatt, more than good enough. If you are trying to run a giant community or mega metropolitan, you may need 1000 megawatt as a buffer load. So that would be needed. So you have scale, you have cost, you have power, and then you have to worry about capacity. How long do you want this puppy to run? For example, in most scenarios nowadays, especially for household applications, if you can buffer the power, for like use all the equipments during daytime and store enough power that you can run throughout the night, you're done, you're sorted. And right now people are doing it. There are people who literally have disconnected the grid. They are literally running on solar only. So, and again, that's happening in India also. So it's one of those things where duration matters for them. Like what is the duration? The duration is during day to night. So that will define your capacity. Now duration is a different vector here, where it's like what kind of time scale we are talking, meaning pumped hydros, batteries, these things are good for day or two. They are not designed for, I'm going to store excess energy from monsoon season for a rainy day. That's not going to happen. Although ironically, monsoon is a rainy season. So let's assume you have a lot of monsoon that gives you a lot of wind power, and then you have winter that gives you a lot of solar power, because again, panels are cooler, sunlight is far more clearer, you get GG amount of power. Now you want to take care of the summer part. Again, that means you have to buffer energy for months. Again, only few chemistries, only few options can do that. This is not designed for that. So be very mindful. That talks about duration. So people learn, we are talking about day night energy storage. We are talking about weeks of energy storage, month of energy storage. Basically, once you reach year, that's a final destination. Once we can reach that point where it's like we can store energy year over year, done, sorted. So these are the 5 vectors that you have to worry about. Basically, what is the scale we are talking about, what kind of cost people are willing to pay for it, what kind of power we are looking at, and what sort of capacity, how long it can run. Basically, power is the generator, capacity is the fuel tank, and then duration is basically how long can you do that. So there are, thankfully, people have starting to wisen up, is that electricity is not a thing that we use. We use things that are done by electricity. For example, you'll go into a basically industrial plant. They are making metal. So they are consuming GG amounts of electricity, bonkersly high amount of energy. So what are they doing with that electricity? Well, they are melting stuff, right? That's what they are doing. They're melting it. Arc furnace. So what if you can get that heat directly? What if instead of storing electrical energy, you store thermal energy? So you basically have a chamber where you just dump excess power, temperature rises up in that system, and then you draw 1500 degrees Celsius heat out of it. You are no longer storing electricity as electricity, you are storing electricity, surplus electricity, as thermal energy, and you directly use the thermal energy. So it's a very viable option. Higher the temperature you can store, the more capacity, useful capacity you're going to get, and more systems can be basically made into renewable system, where you have a giant buffer without costing too much. While in principle we can store all the energy we need on batteries, everything can be done, but yeah, that will destroy the cost part and the planet also. So fundamentally, thermal energy storage is a very good solution if you actually think about it. And Europeans have surprisingly wisen up to this. It took them quite their long time, but they kind of realized it's like, yeah, we're spending a lot of energy just to heat the damn thing. What if we take surplus electrical energy, dump it into a medium, and voila, now we have a constant source of heat, renewable heat, and there is a giant buffer. We do not have to worry about it. Again, there are people working for high temperature heat also. So that will take care of the industrial side also. So thermal energy is a very viable option. So do not just let it, oh, it's not electricity, it's not worth it. Like for example, in my case, let's say I run a ice battery. Again, it's a type of thermal, but running on negative direction. It's like I charge my ice battery directly during the sun, like full daytime. And how does my air conditioner run at night? It does not. I do not have to. I directly run the cooled water from it. So that is one option, direct thermal energy storage. And then you have electrical, which is normal, easy to understand. So what options do we have? Like a lot of options we have. We have lead acid battery. Again, right now I have this. And again, be mindful, lead acid is, while not very efficient, has 10,000 problems. It's one of those puppies that are cheap enough that you can actually do some heavy things with it, and robust enough, reliable enough, and time tested enough where it's like we do not think about it. So it's like, it is one of those things where it's like, just trust it. We run submarines on these puppies. We know these puppies can last. And I have seen like some giant, like recently just went into a location that had like 35 kilowatt, solar system, and a court that I go to that has like 50 kilowatt system, lead acid battery. So lead acid is there. Then you have lithium ion. Now, why don't we switch all things to lithium ion? Again, lead acid has been running for 1 century. So inverter systems and charging circuitry, everything is standardized. Like you do not even have to worry about it. Everybody can repair it, everybody can service it, everybody can mass produce it. We're done. Lithium ion is a completely different ball game, and not to mention it has different systems into it. For example, lithium ion is different from lithium iron. Lithium iron is different from lithium titanate. So that's a hell of a hassle. And for example, to give you a cost analysis, 2 to 3 years ago, I bought 2 lead acid battery because my older lead acid battery died. So I bought 2 X-side 12 volt 200 amp hour batteries. 2 big batteries. That's are my like core of solar as of now. Now these 2 batteries, good batteries, they are running. That costed me around 40,000 rupees. That's a lot of money, like 44,000. So a lot of money. Now, how much lithium I can get at this point in time? Right now, there is one Indian company that is giving lithium iron batteries. Again, that means it's a thermally safer option. 24 volt, that's good. But only 100 amp hour, costing 40,000 rupees. So you see, it's like, now, practically speaking, lead acid is not really known for its efficiency, meaning if you dump 100 kilowatt in, how much you get out of it, it's not that much. Like if you put 100 units of electricity in, you will barely get 70. Lithium ion is far more efficient in that regard. So that 100 does not mean that bad. It's not half. It may be like 75% of what I can get. So you see, we want everything. It's just that, can you afford it? So lead acid is still here. It's gonna stay here for a while. Lithium ion slowly coming in. It's gonna get here for again. It has already started to reach, but it's gonna take a while to trickle down because cost is high. Then people also are looking into sodium. Now be mindful. This is a very serious misunderstanding people have, is that cost of material is not the only thing, and many times it's the least important thing. Basically, silicon is not that expensive, sand is not that expensive. It's just that going through lithography process to make into a solar panel or make into a GPUs, that's the expensive part. So same happens with sodium. Oh, sodium is cheaper than lithium. Yeah, that's not the reason why lithium ions are that expensive. It's just that the investment that went into making the production site, that puppy requires the payback. So again, same thing will apply with sodium. And not to mention, you have to now redo everything. We already redid everything from lead acid to lithium. Now we have to redo again. I'm reasonably sure in few years we will finally give up on battery controls and be like, okay, here's a freaking computer, program what the hell you want to do it with it. Because lead acid was like a dumb circuitry. Lithium ion, we had dedicated circuitry. And again, if we keep changing from like this to that and all that, people will simply give up. Here's a microcontroller, code it what you need to. So lead acid, lithium ion, and sodium, these are options. In terms of heat energy, sand, a cheap and effective option. Fire brick is a bit hotter temperature option, meaning sand and gold is very good for low grade heat, meaning heat that is less than 100 degrees Celsius. So you heat it up to 600 degrees Celsius and drain heat to heat up swimming pools, heat up homes, things of that nature. Fire bricks, it's more for industrial use, where you heat it up to 1500 degrees Celsius and leach as much heat as you need for your process. Then you have graphite, that's the daddy heat, that's this puppy. This puppy goes to 3000 degrees Celsius. So in that 3000 degrees Celsius, now you can actually melt metals reliably. So that's there. So we have these three primary options. And then you have pumped hydro, which is the big unit where it's like, I want 3 gigawatt hour capacity. I want 5 gigawatt hour capacity. This is the only way right now you can do it. Then you have hydrogen. Now, hydrogen is not a very good energy carrier, but it is a very useful thing for our industries. Metallurgy consumes it like there is no tomorrow. A production of basically other stuff like ammonia and basically a lot of food processing, they consume hydrogen like there is no tomorrow. So if you have surplus power, converting into hydrogen is like a sinking process. Like, and be mindful, we do that. It's a normal thing in countries to do, whereas like they have surplus production, they dump it into aluminum. That's how we do it. Like aluminum's furnace or like smelter, so to say, consumes so much power that it's a very good offset. Whereas like, hey, we have surplus power, dump that into cheap aluminum. So we can do the same thing, dump it into cheap hydrogen. We need it for multiple fields, not as an energy carrier. Let that be very clear. Not as an energy carrier, but as a consumable. So it's a very good thing. And then you have gravity energy, so where you just pull something up, let it drop, almost like pumped hydro, but generally you're talking about a solid. Now I have lost hope in this gravity part, but people are still trying, and it may have some minor use cases. So there are a lot of types. You see, it's not a black and white, it's like this and that. There's a lot of options and a lot of reasons for those options. 5 vectors, you have to balance 5 vectors. So here's the deal. Physics, engineering, economics. Whether you succeed or fail directly depends on a daddy layer, which is economics. Now, economics says one thing. If you have higher round trip efficiency, meaning if I buy 100 unit of electricity, it does not matter what unit it is, kilowatt hour, it could be megawatt hour, gigawatt hour, does not matter. So I buy the energy, how much can I return from my system? That is the core. The higher that number is, closer to 100%, the better it would be. Now again, lithium ion battery is one of the best in this regard. It can almost touch 95 real world use case scenario, but again, it does not scale up very well. So if you want to scale up to daddy sizes like a pumped hydro, these puppies can easily go up to 50 plus to 70 plus. But again, you do realize you have lost a lot of power in just the conversion inefficiency. So you need a requirement, a bit of more incentive to make it financially viable. So what does that mean, financially viable? That simply means your market, basically the people who are dealing with energy purchasing every day to day, they must have price volatility. Meaning if it's a dictatorship where government is like, no, this is the law, yeah, it's not going to work. It must allow price flexibility. Now you may like, doesn't that cost issue? Yes and no. If done correctly, consumer gets a slightly higher price, but they get quality electricity without any issue. And again, it's now incentive for dispatcher and for the power producers to be more as optimum as possible. It reduces waste and has yielded a very good result. Again, it does require some wisdom. It doesn't, you do not want to go free for all. You want some wisdom to it. But again, if you have price volatility, it does solve a lot of problems. So what does that price volatility mean? It simply means buy for cheap, sell for profit. Meaning during, let's say, there is no demand on the grid, but power plants are still running. They have to run, otherwise it will be a loss operation for them. So they sell power for very low price. Like, hey, please buy it, man, please. So at that time, you buy it. Let's say you buy it for 1x. Now then you have surge demand during, let's say, springtime, surge demand. You need again, power plants have already reached 100%. Now dispatcher is stuck. Is like, what the hell I do? Now you sell the power for 5x, 10x. Like, yes, the power prices go fluctuate that much. So that's one of the very easy way of taking care of this situation. Selling, basically buying for cheap and selling for profit. Now, this whole idea seems crazy. It's like buying power for cheap and selling it for high, but it was done. It was done for a very long time. It's done for so long that it's a system right now. Meaning this happened during nuclear fever. During 60s and 70s, people kind of got cuckoo with nuclear and they thought this will be the future. A lot of nuclear power plants being commissioned and a lot of them came online. There was a problem that nuclear power plants do not like to throttle that much. They're not as flexible as coal power plant or gas fired power plant, so they need to be on constant load. So problem is that if you have constant load, either you have to make too much of it, basically, so even the peak never exceeds your total generation, but you will have so much surplus, you would need way too much ability to just burn the energy away. So somebody came up with a clever idea. It's like, hey, because again, X variable is happening, meaning during surplus you have almost negative price, and during peak you have very high prices. What if we make medium size? Basically we find the average of it, have some buffer on it, and make that much. Now those power plants work 24 into 7 into 365 on a fixed load, what we call base load power supply. Do not have to worry about it. So that's there. But how do you balance it? Well, here's the deal. You built giant dams, so to say, and this is a dam that is next to an ocean. So idea is, or sea, the idea is, you during this time, basically you have surplus, you sink the energy into this thing, and they run the generators as pump the water from the ground reservoir or the sea level to higher elevation. They pump that puppy up. So now what happens during when you are exceeding what the nuclear power plants can produce? They run in reverse as a turbine and generator, like a hydro dam, and voila, the energy goes back into the grid. Now these are generally designed to do it every day, and it does work. We have been doing it from 1970 to 1980. A lot of these puppies were built, and all of them are still working. Most of them are still working. Literally only few of them have been decommissioned, and majority of them gone renovation, upgraded, so their cycling efficiency has improved, and everybody's like, oh, we have the technology to sort basically, renewable intermittency. Like, this puppy was designed to solve that. This was the original problem solver. And in terms of capacity, they are measured in megawatts. Like, everyone's like, oh, Elon must build 100 megawatts battery banks. This puppy is like, bro, been there in 70s, done that. We measure in gigawatts. And not only gigawatt of power, also in gigawatt of capacity. We done, we sorted. Like, that's how we done this. So it's a common system, and be mindful. Whole Europe went cuckoo with this. America went cuckoo with this. Japan went cuckoo with this. China is going cuckoo with it. So that's the only way right now on large scale deployment that this is there, where you can store gigawatts of power and have enough oomph that you can actually take care of a metropolitan city. So this was the first time humanity ever attempted this, and it did work out. It's still working. By the way, the power plants that were supposed to feed this, most of them will be decommissioned very quickly, and some of them are already decommissioned. This just got an upgrade. So what does this mean? This simply means the bigger the price gap you have between the surplus and the basically peak demand, the more likely it would be you can build this sort of system. Why? Because again, the profit is directly proportional to the round trip efficiency and what is the X variable. So as of now, the demand of electricity, basically the price on peak time is not that high. However, surplus is negative, meaning at that point you can actually get paid. So the government does not have to shut down the grid. People will willingly pay you, so they do not have to shut down the turbines. Yes, that's the thing. I did not even realize that's happening for past 2-3 years. It's a thing. So at this point, even a very chump change, like you are buying energy at almost free prices, very little price, and even if you are wasting 50% of it away, you still have enough energy left in the bank where you can dump it and make profit. Basically take energy during the day, sell it during the nights, enjoy profit. Again, exactly what these things are doing. So it's a very interesting way where we can solve all of this system financially without requiring incentive and all that. Again, it may require incentive to smooth line the process, some low interest loans too, because again, these are big investment. So those things are there. But the bigger the gap between the lowest point and highest point, the more profitable it will become. And again, you have to worry about all other vectors also, like state of charge, how much you can deplete it. Again, this in principle will have full capacity, but they will never deplete it to full level. Depth of discharge, how low you can allow it to go, and round trip efficiency. Another aspect is self discharge rate. Like, these things are awesome, but they are not designed to be handling power for season. They're supposed to be cycled day in and day out. Week can be done, but if you are expecting it to, like, what if I store excess solar energy during the summertime and then use it in winter? Yeah, it's not designed for that. We need something different for that. So be mindful, these are the curves of power draw during summer, during fall, during spring, during winter. You see, it's completely different. That's why you need a buffer. So economics is there. Let that be very clear. If you're like, oh, it will destroy the grid. We had the issue solved in 1977. And many of them exist. It's not just one. There are many of it. This one I like simply because it's not even touching a water reservoir. It's just like ocean. Go up, go down, go up, go down. Now, one fundamental thing you have to understand, there will be growing pains. Let that be very clear, as clean cut as it can be. The whole renewable energy sector is completely new to us. Ironically, this was the first energy system we used. We used water wheels, we used wind turbines to do grain crushing and all that. So we went from those things to fossil fuel, now going back to them. So it's a completely new system. And we have to change our thinking, how we are thinking about our current infrastructure, where it's like, you have centralized generation and distribution. That's not gonna work. Basically, we have to fundamentally change. Like, this is here, this is real, we have to change now. Like, few years ago, basically the first time I got my internet, that I was in class 11. That time, if you had told me I could have 2 kilowatts of solar in my rooftop and make sure that my refrigerators, most of the heavy loads other than air conditioning and washing machines, will be sorted, I would have laughed you out of the room. But now that's a today story for me. And again, my original plan was getting a 10 kilowatt system, so completely include the air conditioner and all that jazz. It can be done in principle. It's just that I don't have pockets for it. So it requires a different kind of thinking. That was unheard of. In 70s, people were like, what the hell? Now we are doing it. There are people who are doing it. There is a hospital in a basically remote village where they did not even bother to get an electrical connection. It was such a hassle, such a pain, and not to mention the uptime was so poor of the electrical grid. They're like, hey, what if we don't bother? Because again, if we get electricity, we have to buy a generator, we have to have fuel for it. What if we have the generator, fuel, and huge as solar and huge as battery? So generator we still run periodically, and again we charge the battery. So thinking have to change. Like how these hospitals changed it, we have to change our thinking. If we do not do that, we'll be stuck like, what if we have generation and all that? Yeah, that's not gonna work. We have to change our thinking. Now, we will face issue. Let that be fundamental. People are like, oh, this solar caused this issue, wind caused this issue. Of course it did. We've been here, done that. What do you think? Our national grid is just ta-da! That's how it happened? Hell no. There were hundreds of issues. Regional issue, local issue, national issue. It's a common thing. Look into the history of it and you will find more than enough. Where it's like, okay, this power plant went boom, this substation went kaboom, this went boom. This is a normal thing. We deal with it. There is problem, there will be downtime, and we have to deal with it. That's what we call growing pain. For example, somebody built a bridge, wind just like yeet that bridge. Did we stop building bridges? Hell no. We learned from it. We improved it. And then like, we got you, fam. So that's the fundamental reality of it. There will be pain. Like if you are trying to run away from it, you are in the wrong world, my man. So, and a lot of tricks will be tried. Let that be very clear. That's how we solve problems. Like we built basically a mobile phone that was the size of a brick. How the heck we went to smartphone? Hundreds and thousands of people working on hundreds and thousands of ideas. And over time, evolution happened. The weaker ideas died out and voila, smartphone. Same thing happened with RAMs. Like we started with DDR RAM, like whoa, DDR2 RAM, ultra whoa, DDR3, DDR4. Heck, I have DDR5 right now in my computer and DDR6 in my graphics card. So let that sink in. Like it's one of those things. That's how it happens. Every evolution happens. Solar panel. I just went to basically an event, engagement event, that remote location. It had 35 kilowatt solar system. It just had it. It's like, yeah, who cares? Like we are not even, what the hell? You have 35 kilowatt of electrical generation every day for almost 250 days out of 365 days. That's a generation. That's a boatload of electricity that they are like, we got this, fam. So fundamentally speaking, it's the way of life. We're gonna have growing pains. Anybody's like, oh, this will not have problem, or it's too scared of it. Both of them are wrong. Like you gotta have a problem and you have to deal with it. So Inaction is not acceptable at this point in time. That's the fundamental weak problem here. There are many times politicians are scared, and again, publics are also scared because again, somebody's like give them, oh, if everybody installed solar, the grid will collapse. Again, it won't. And if there will be issue, it will be a staggered issue. It will like, okay, this session has that issue. Some engineers will come and like, we can solve this. Other issue will happen. Some are like, we can solve this. It will not work. Something else will be tried. It will. That's natural. How the heck we went from this? Okay, we have a problem, we solve it, to like, oh, what if we don't do anything? That's not acceptable anymore. We have to deal with the problem. We have to solve it as it comes forward. Again, bridges used to get blown off by the wind. Now we don't even care about hurricanes anymore. So it's one of those things. Growing pain is a part of it. Fundamentally, you have to accept it, willing to go the extra mile. Only then you can deal with it. And if your country or culture or the region that you are living in does not take actions, just like, let's just push it away, it's not acceptable. Again, for your children. If you don't give a damn about your children, but if you do, inaction is not acceptable anymore. So what can we expect in the future? Well, here's the reality. Remove the religion, remove the boundaries, remove blah, blah, blah. But fundamentally, humans are problem solver. You throw a problem at us, we're going to solve it. Now, the only weak link is two problems, is bitching and running away. Now, bitching and running away are two kind of different scenario. Running away is basically like, what if I don't solve it? Like, everybody's like, okay, this is a problem, but they are creating meetings with extra meetings, with some extra meetings and blah, 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 blah. It's not actually doing anything. That's a running away, but again, with butter masala. And then you have bitching. Bitching is like, people are like, whenever I talk about like, how seaweed biofuel can actually fix the CO2 emission of aviation. They're like, oh, but it has emission. It's like, yeah, the other option is you let the planet burn. Let me level out here. Option A, you don't do anything and the planet burns. Option B, you do it and now you remove the CO2 problem. Again, you work it effectively, try to reduce as much as you can the emission part of it. But again, you will reduce the problem and make it far more manageable. But you are bitching about it. It's like, what the hell? It's like, no, there is no. It's like you take an action and you just go step better. You do not go from DDR RAM to DDR7 RAM. That's not how it happens. You have to go to DDR2, DDR3, DDR4, DDR5. That's how it happens. You do not go from, I built a plane from like, Wright brothers and voila, SR-71. That's not how it happens. So as long as you can keep people who bitch in control and keep people away from running away, because again, this is a very serious reason why Indian Railway is not a flagship as it could be. Even though we have the money and the scope and all that, it's just that every time engineers in India, they came to railways like, hey, we can build awesome bogies for you rather than buying it from Switzerland or patenting the design and all that. Is they're like, give me 25 years of safety data, only then I'll buy it. It's like, how the heck do you think Japan built it in the first place? Like every time somebody tried, it's a meme. I hope it's a fake meme, but I know too well to know that it's not. But I hope is that every time some company came, I was like, hey, we can build it indigenously. The government's response was like, give me 25 years of safety. It's like, that's not how things work. You test it, you verify it, you improve the process, you test it in staggered ways so people's life are not put in unnecessary risk, brick by brick, day by day. You test it, you improve it, you refine it. And if something bad happens, God forbid, you improve from it. That's literally how Europe got a railway system. That's the literally reason why we are buying things from Japan. So it's one of those things, like you have to make sure people do not run away. You have to make sure people are not bitching. It's like, is it better than the last option we had? Yes, move forward with it. And another aspect is engineers and scientists. They are the two people who will always say nuclear will solve all the problem. Yeah, as I specified, physics, engineering, economics. So accountants will take a RPG and blow it up your ass if you ever said the nuclear can work for civilian. Let that be very clear. Do I want India to develop nuclear technology that's working with thorium? Absolutely. Why? For our navy, for our military operations. You need good energy sources for them, and they do not have to worry about ROI, return on investment. Now, the world is not in 70s anymore, and I have no idea how the heck scientists are not getting it. Because yes, dear, now you go to the government and it's like, give me $6 billion, I give you 24/7 power, little bit of power, let's say 2 gigawatt of power. Okay, cool. Here's the deal. Right now, same company can go with the government and be like, hey, give me this much power, I'll return all the money that you gave me in, let's say, 8 years. And I give you a lot of power, lot more power, like exponentially more. Like at 8 billion-ish, you can easily build a 6 to 7 gigawatt of solar farm. And yes, we have enough free lands. Have you looked into deserts in a Google map? Lot of it. And again, that amount of money is so much that you can build a substation and grid infrastructure needed for it. We're there, we're done, we sorted. And again, India did build huge farms. We have farms that are measured in gigawatts. We built it, it sells the power, the ROI happens. Problem solved. And again, the energy storage, again, that's awesome. That's an awesome problem to have. And then again, more engineers will come together and they're like, okay, this will try for energy solving issue. Energy is like, voila, some will work. So ROI does not happen because again, there is competition from solar and wind. That was not there in 70s. Now there is a competition. Heck, I can, again, if I were not as poor as I am right now, I would have literally removed electrical connection from my home. I would have a small backup generator, which again, I would run once a week or so, not even a week, 15 days. So once a fortnight, and voila, I have a completely sorted system. Solar is there in one of those blue moon scenario where there is not enough solar in India. Somehow I can just like, run it on generator. And again, if something really bad happens, downtime maintenance, I have the generator. And it will cost me less than what is costing me right now. So that's the reality of it. World has changed from 70s. Everyone's like, what we can take care of. And I'm not even touching the safety aspect. Let that be very clear. I'm not even touching it. That's just the cost aspect. And like, the American nuclear power plant is very cheap. It's not. What it is, it's a fixed cost, contract cost where the like government bought the energy for I think 50 years at that fixed price. So people are getting it. And people are like, why the heck inflation is going up? Yeah, because your government has to now bail that puppy out. It's already bankrupt. It's just that disconnect happened, whereas like, instead of payment going from left pocket, is going from right pocket. People are like, see, nuclear is cheap. It's like, no, it's not. No, it's not. That's why people stopped. We've been there, done that, tried it. We've done that. It's not there. And again, compare it to dropping price of solar. Yeah. Compare that to reducing cost of off-grid wind farms. No. And again, reducing cost of high voltage direct current electricity transfer. No. This does not stand. Nuclear does not stand anymore, financially speaking. Solar, wind are getting cheaper. Again, projections are it can go even more cheaper. Solar can, the moment mass production of bi-junction solar panels happens, bi-junction as in like dual junction, so to say, pardon me, dual junction. Right now we have silicon single junction. If we put another junction on it, the efficiency can jump to 30 or 35%. That will be like shout out, take money. There is so much scope. There is no scope in nuclear because again, everything you do to nuclear makes it idiotically expensive. Because again, children think, oh, alpha, beta, gamma radiation. It's like that. Those are puppies. Those do not bother you. What bothers you, the daddy radiation, it's called neutron. It makes other things radioactive. It will never be cheap to handle that puppy. So solar and wind are getting cheaper yearly, year by year. Like here's the deal. When I got my first computer, at that time I looked into solar panel and all that. The best thing I was hoping that my emergency could run on solar. It was that expensive. Right now I literally run heavy loads on it. My computer, this whole system is running on solar. I do not have to worry about it. So fundamentally, power curtailment is real. Like you are like, oh, we're going to have solar energy. We have power curtailment, meaning we already have both part of the energy spectrum economically sorted. Now we have to jump into the energy storage part, which mind you, nuclear already provided. Which people are just like, but what if this, what if that? It's like, what if you solve it exactly how you solved it in 1977? So power curtailment is here and we can solve it. And this is the perfect market condition. And I am genuinely shocked. Humanity is like, look at this. This is awesome. And then I said like, energy storage. No, nuclear. It's like, only people who like nuclear is scientists and engineers because they do not have to worry about the cost of it. Because again, if you ever task any engineer and scientist with the cost of something, engineers are somewhat better. Scientists are like, if you look at the cost of, fusion reactor, it's like, all of them will be poofed out of existence. So that's the reality of it. Right now, this is a good situation for us to have a curtailment as an issue, to have a deficit as an issue. All of them could be happening in a day. That's a very good issue to have. We are working on it. We can solve it. And science and technology is there. But just what works economically, what works scale-wise, economically scale-wise, all of those things will be worked out. As long as we do not bitch about it and do not run away. Solve these two problems, everything else will fall in place, eventually less than 5 to 10 years. We are building this. We got this. We got this. We sorted. We good. So this was my presentation on the energy storage potential. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.